Hi everyone, and welcome back to our class in Artificial Intelligence and Machine Learning in Finance. In the last video, we've seen the maximal margin classifier. And if you look at this slide here, we saw that the maximal margin classifier is actually quite sensitive to new data. If we add new data points, then the decision boundary, which is the line here, for example here, is quite sensitive to these newly added observations. So the question is, can we make this classifier a little less sensitive to new observations and a little more forgiving? And this is where we actually now arrive at the so-called support vector classifier. It's not yet the support vector machines that we want to talk about in this section, but it's the support vector classifier, which is also usually summarized under this name support vector machines. So the solution is we use a classifier that allows for some observations, not all of course, but for some observations to be incorrectly specified and classified. And you can see this here. For example, if we add this observation 11 and this observation 12, even though 11 is red and 12 is blue, the decision boundary doesn't change too much due to these newly added observations that make the decision boundary no longer a separating hyperplane. So we want to have a little discretion when it comes to the classification of the observations, and this is what the support vector classifier does. So the difference to the maximal margin classifier can be seen here in the optimization that leads to the support vector classifier, or the support vector hyperplane that we use to classify. We again use our constant m. We have our parameters beta 0, beta 1, etc. for the hyperplane, and now we have additional variables epsilon 1 through epsilon n, and we maximize m with respect to these parameters. We have the same constraint in line 28, that is the squared coefficients all add up to 1. And the difference now is, first of all, that the hyperplane and the observations should not be exactly higher or lower than m, so it's not like we are again looking for a separating hyperplane, but we have some discretion, and this error that is possible is actually included here with these so-called slack variables that allow the observations to be on the wrong side at least a little bit, what actually happens here. So we would expect 11 to be on this side, but it's okay that it's actually a little bit off and a little bit above the hyperplane, so then this would be captured in the slack variable, and we allow, or we demand of course, that the slack variables are non-negative, and we have an additional hyperparameter which is c, so that the sum of all those slack variables, in other words the sum of the errors that we allow, this needs to be smaller or equal than c. So c is of course a non-negative tuning hyperparameter. It's chosen via cross-validation, and m is again the margin. So this is the support vector classifier. We see 4 different support vector hyperplanes in these plots, and as you can see from the title, these plots result from different choices for the tuning hyperparameter c. For example, the largest value of c was used in the top left panel. Smaller values were used then in top right, bottom left, and bottom right. So we have 4 different values, and actually when c is large, then there is a high tolerance for observations being on the wrong side of the margin, and so the margin will be very large. And as c decreases, as we reduce the maximum allowed sum of errors, as c decreases, this tolerance for observations being on the opposite, on the wrong side of the hyperplane, decreases, and the margin narrows. So you can see this here. This is, let me see, this is actually the margin from this side and from this side. And as you can see, it is reduced in each plot, going from top left to bottom right. Now, the question now is, Are we done? Well, actually no, because is a linear classifier always warranted? Well, And if you have a look at this plot, you can immediately see no. You can try your best at using a plane, a hyperplane, that is a line here, to separate the blue and red points. Then, for example, if you were to use this line, then you have those observations here that make a problem and cause a problem. You can use a hyperplane like this. It doesn't really help. What you really need is something actually that is nonlinear. For example, it could be something like this, or it could be something like this. Could also be useful. So a linear hyperplane is not warranted here, and we need sort of a nonlinear classifier, and this is where we finally get in the next couple of slides to the support vector machines. Well, the support vector classifier is a linear one. So how can we automatically convert it to a classifier with non-linear decision bounds? First thing we could try is that we again maximize the margin. We use the betas, the epsilons, and m as our parameters. And we now say, okay, we are not using a hyperplane, but for example, as you can see here, this is again the response being -1 or 1, the margin, and we allow a certain error in the slack variables. But here in parentheses, where previously we had a linear hyperplane, we now allow what is a polynomial function. So just like we did with polynomial regression, we allow the decision boundary to be a polynomial one. And this is one way of doing it. Problem is, it might not be enough. A polynomial regression, we've seen that adds some flexibility to our model. Same here, but it might be that we need more non-linearity. So how can we achieve this? First of all, recall the standards, in this case the Euclidean inner product for two vectors, xi and xi bar, dash actually. You have the scalar product, the Euclidean inner product of two vectors, and we need this because the linear support vector classifier can be represented. It's just a different representation, different way of showing what the support vector classifier looks like. With n parameters, alpha I actually is what? It's the hyperplane is given by beta 0 plus the sum of parameters alpha I times the inner products of x and xi. So in other words, we can use this representation. Where did I get it? This here, which is, it's a linear function, it's a linear line, a plane, or whatever, and the hyperplane can also be represented in this way. So instead of using beta 1 times x, beta 1 x1, beta 2 times x2, and so on, we can also use the inner products. We get a different set of parameters. Now these are alpha I and beta 0, of course. And to estimate these, we only need those n times n minus 1 divided by 2 inner products between all pairs of training observations. At first, this sounds like a lot. If we are looking at a big data sample, then obviously if we have like 1 million observations, then we would also have 1 million, 1 million times almost 1 million divided by 2 inner products, and we have n observations and n parameters. However, alpha I is non-zero only for the support vectors in the solution. You can again see why they're called support vectors, and this means that we actually don't need all those n parameters alpha I, but we have a much smaller number of parameters that we need to represent the hyperplane from the support vector classifier. Now, why do we need this? Why do we need this different representation for the support linear classifier? Well, the linear support vector classifier can be extended in a very simple way. And how? We replace the inner product with a more general so-called kernel. What is a kernel? A kernel K, at least in the context of machine learning, it has slightly different meanings in different parts of mathematics and statistics. But here in the context of machine learning, a kernel is a function that quantifies the similarity of two observations. So we have two observations, x1 and x2, and a kernel is a function that in some way measures the similarity. Could also be the distance between those 2 points, and this is what we call a kernel. Quite clear, in the case of the inner product, this is of course a function that measures the distance in the Euclidean space between those two vectors. So we need to replace the inner product. We need to replace, where's my cursor here? We need to replace the inner product here with a different kernel, and then we get a more general extension of the support vector classifier. And this is what finally is a support vector machine. We can use different kernels. For example, we can use the linear kernel. We can also use a polynomial kernel of degree D, or quite often use the so-called radial kernel or radial basis function kernel, which is given in equation 37. So these are different choices for comparing xi and xi dash, two vectors. And if we now substitute the linear kernel by, say, the radial kernel, we get a different classifier. And if we substitute the linear one with a non-linear kernel, the resulting classifier is known as a support vector machine, or SVM. In equation 38, you see we now only speak of a general kernel K. And what is important is, as I mentioned before, we don't need all n parameters, because these parameters alpha I will be non-zero only for the support vectors. So the set S that includes the indices for the support vectors is usually much smaller than n, and this representation is only we only need these indices in the set S. So that's the set of support vectors. That's a support vector machine, substituting the linear kernel with a non-linear kernel, and what we get is a much finer way of classifying these observations. On the left-hand side, you see a polynomial kernel. You see that we have our observations here, and we would have liked those red observations to be separated from the blue ones. And the polynomial kernel does this. And actually, as you can see on the right-hand side, the radial basis function kernel works even better. So these are support vector machines. They are estimated in a similar way as the support vector classifier. And all these classifiers, actually the maximal margin classifier, the support vector classifier, and these more general support vector machines, usually they are all summarized under the name of support vector machines. So these are SVMs, that's the theory, and in the next video we'll be looking at some applications.